So the program for the rest of the morning is a couple of short panels. The first panel is really about applications and opportunities. That is, what are we going to do with all this seemingly great stuff? And what are we going to do that's different from what we have been able to do in the past? And the second panel is about the ecosystem. What are we going to do to make it reasonable for mere mortals to get this done? And I've got great panelists this morning, and I'm going to run through them in the order that they appear on my piece of paper, just to make it difficult. So we have Faria Said Araghi, who's the Senior VP of Innovation and Advanced Technologies at NXP. He was the CTO of IoT and Security. He worked at InvenSense, SciTime, Rambus. He was a researcher at IBM TJ Watson, working on CMOS SOI. He did his PhD at Berkeley. He's sort of been around. and kind of done it all from semiconductor physics to, security software. So, I think he's probably pretty dangerous. On the far end, we have Edith Beignet, who's the Silicon Research Manager at Facebook in the AR/VR organization. She was previously the Research Director of the IC Design Division of CEA Leti in France. She's been working in low-power digital and mixed-signal architectures and around emerging technologies, network on chip, for quite some time. Ofer Deckel manages the machine learning and optimization group at Microsoft Research. He's kind of a hardcore machine learning algorithms, algorithm engineering, statistical learning theory and optimization. He has a PhD from Hebrew University. And Christoph Lang is the Director of IC and Wireless Connectivity at Bosch Research and Technology Center here in Sunnyvale. He's responsible for research groups working on mixed signal ASIC, wireless connectivity, DSP, medical diagnostics, and other things. He's been deeply involved in sensors, especially motion sensors. So as we start to talk about this, I think that one place to start is with a bit of, I'm going to start with a contrarian view. From the standpoint of applications and opportunities, why is tinyML different from any other kind of embedded software? I mean, it's really just a way to express intent and put it on a piece of silicon and deploy it. So what's different? What is fundamentally different about the upside opportunity or the types of applications that we will do with this new computing model that we couldn't do with all our old computing models?
Me first?
Yeah, why not? Okay. You look like you got something to say.
So, yeah, thank you very much. I think that, so here's how I think about it, right? So when I think about resource constraint machine learning and developing algorithms for this area, we think about having compute constraints and memory constraints, but you can always trade those things for more power, right? If I have more power, I can put more processing, I can put more memory. And if I'm trying to build a device or something that I can tether to a wall and get stick it in the wall plug, then I'm good. I have infinite power. I can put as much compute and memory as I need, and I'm done. So let's put that aside. I also want to put aside anything that has to do with doing tinyML for the purpose of making things cheaper, because I don't understand pricing and I don't understand how to how things are priced and I don't understand money. So that's not a good reason either, right? So we're talking about something that can be tethered to a wall. So we're talking about something mobile. And I need it to have power, and I know how to make something that's mobile, have power. I put a battery. If I need more power, I can put a second battery or a third battery. And now I get to the first thing that I can't trade away, which is size and weight, right? So these are the real resources, when we talk about resource-constrained AI devices, to me, the constraints are on size and weight. That's the primary thing that we can't trade away for the next thing. When I think about size, I think primarily about things that I would need to carry in my body or on my body. And these are the kind of applications that I think that we can't do today because we cannot have this kind of AI, carried around on us. And I'm not really thinking about, maybe the more, to me, a little bit more boring consumer devices like watches and glasses. I'm thinking about things that are really either on our body or in our body, right? So almost body augmentation, kind of cyborg type of technology. We already use a lot of technology to modify our bodies, right? It's not this new controversial thing. My dad has a hearing aid, which is deep in his ear canal, and he can't control it because it's embedded in there. He controls it from his phone. This thing has different algorithms. It has a different algorithm for a conference room or for a rock concert or for an intimate conversation, and he changes the algorithms with his phone. I lose my phone 2 or 3 times a day. So I wonder what my dad does. I mean, does he stop hearing when he misplaces his phone? So of course we need, these things to be able to have some intelligence. Either we control them intelligently or they understand where they are and so on. The people have pacemakers in their heart. And other devices that are embedded in our body. And I think that, in 10 or 20 years, I would bet that we will have many, many AI devices either, in our body, doing different types of manipulations, little robots going through our digestive system and looking for polyps and cysts and sewing up little tears. If we're talking about, other kind of sensors that could be embedded in our lungs. I mean, anything that doesn't hurt, pretty much any orifice in my body, I would be happy to stick some AI in there and make my life a little bit better. So that's what I think of when I think about small. And then
we're going to need to move along.
So let me just say one last
Let me
sentence.
take a slightly different direction, maybe. So besides wearables and where we stick the devices for a second, there are, I think, actually, the one very critical area is really IoT. And when you think about IoT, by definition, we are saying that these devices are going to have some amount of intelligence, some amount of contextual awareness, but at some point, eventually, they're going to connect to the network. And I think where machine learning really helps is that these devices are power constrained, and determining when these devices need to communicate to the mothership is extremely critical, because by definition, these devices are battery operated. I'm not talking about only wearable devices you have yourself, but maybe in industrial applications, in agricultural applications, that you have sensors that have to stay, as I think Chapel was describing, or the Dennis's example was, that you are still staying in the field sometimes for weeks or months, and deciding that where there is a significant activity in terms of the sound or other types, that you have to wake up and actually communicate is extremely critical. Because in majority of these systems, actually the communication power is the dominant factor. And I'm not talking about maybe going all the way to the cloud. Even if you have a mesh network, being BLE or something of that nature, you're talking about tens of milliwatts of power. So which is, unless you are heavily duty cycle and only are determining critical activities, and hopefully machine learning allows you to determine what that critical activity is, you will run out of battery very quickly. So I think in that sense, machine learning becomes a critical factor, not just a nice computational addition to the system.
So in a sense, you're saying that by putting an enormous amount of compute at the edge, we overall save net energy resources at the system level.
Exactly. To actually make it work.
Yeah, interesting.
Maybe
Christoph.
I can contribute a few applications as a response to Kurt Kreuzer's request regarding automotive. So I have my key fob here with me, and many of you have one of those flag key fobs that you use in order to access your car. And I believe that is a good starting point for a story of applications that all revolve about this theme of using wireless connectivity as the sensor. So the connectivity actually becomes the sensor. And so if we think of what's currently happening, there's a movement in the industry towards actually putting different kind of radios on those key fobs. It's ultra wideband. It makes it more secure. And for that, you need to have in the car like a few of anchor nodes that communicate with your key fob, let's say 6 anchor nodes. And now what we have been working on is like taking one step ahead and thinking, if those anchor nodes are in the car, what else can you do in such an environment at super low power consumption all the time. And there are a few things that come to our mind. Like one is intrusion detection or occupancy detection. If you have those anchor nodes in the car that communicate with each other, and now you have a person sitting in the car, it's basically like a big bag of water in the car, and that actually disturbs the communication between those devices. It dampens some communication, it reflects some others. And so you can then actually start detecting if there's a person in the car that's not supposed to be there, or if like a child is left behind. And then you can go one step further and you say, okay, this, like if it's the person is breathing, so there is actually like a characteristic pattern on the disturbance, which is correlated with the breathing rate. So you basically have a vibrating bag of water in there. And then you can start measuring the breathing rate. And you can even go one step further and you start measuring the heart rate, all based on the way this wireless communication is disturbed. And the power budget for such applications is like less than 2 milliamps. So you have to do this with less than 2 milliamps per node. And so I think that is one area which is currently not completely solved, where where the whole community actually can contribute to.
Yeah, right. Go ahead, Edith.
Yeah, so you were asking about new functionalities that tinyML could bring. So what I think is that overall the functionality with deep neural network is there. We have many things, but the really new thing that tinyML could bring, if we think about AR, VR, or IoT, whatever, is that we could have systems with a way more flexibility, meaning that instead of using a single neural network for detecting, recognizing everything, the idea of dynamic neural networks or splitted architecture in where you can have a very small network just for detection at very low power, but already giving enough information, even at very low accuracy, it's already something that could bring a lot of information, especially when you're thinking about sensor computation, multimodal sensors environments. It's something really important. This flexibility in having something that is very low power, but probably most of the time giving enough information to the user or to the application already to do something, and then maybe extend it to something more complex, more powerful when you have the ability to do it. I think it's really a functionality that has to be brought with the tinyML, and I've seen pretty interesting talks yesterday talking about adaptivity, flexibility, all these things. I think it's really one of the key of something we can bring.
Great.
I think I build on that. I think it goes back to the issue of communication. That the communication power is going to be a huge limiting factor when you come to all these intelligent devices and the information that you are gathering. So sending less of that data to the cloud or to the next node or to the aggregator is the name of the game. So how much of that you can do intelligently in the device, and the more of that you can do, and you can do it at extremely low power that these devices have, you actually solve the overall ecosystem problem.
Yeah. There's a certain irony in the fact that, IoT concept over the last 10 years has evolved as, we're going to hook up everything to the internet, and we're going to use the intelligence of the cloud in order to provide all of these local experiences. And really what I think you're saying is that, no. I mean, a little bit of connectivity to the internet is good, but it's too expensive. And we have to it's actually cheaper to move a lot of that functionality to the edge.
And not only too expensive, I think also for privacy. So, at Facebook, we are really sensitive with the data.
Yeah.
And also it's something you don't want to send all the information, all what you get in the glasses. You know exactly where the user is, in which environment, with who. You don't necessarily want to send all this to the cloud. Maybe you want to compute things to also to have some cryptography inside the glasses, and then just keep what is important in the glasses and compute everything else in a stage or something else.
I think that's actually a double-edged sword, because I think actually exactly on the issue of privacy, as you are saying, if you can do it locally and you never need to go to the cloud, it's perfect. The problem is that if you try to now do a complete privacy protection, and not only the link is encrypted, but actually the data never is decrypted at the cloud. You are not assuming the trusted third party, then again, relying on something like maybe fully homomorphic encryption or Galway circuit and so on, that requires enormous amount of computation. And normally these devices, the challenge that they have, they don't have the computation power. So to me, both security and privacy are kind of a unsolved problem for tinyML devices.
I have one comment. I think that we're confusing two things that are different. I think one is putting AI on the edge, and the second thing is tinyML. Putting AI on the edge, we could talk about this, and there are very, very good reasons. We've mentioned, I think, two of them here. I mean, typically, I think about bandwidth, latency, privacy, compliance, and reliability. So, each one of these wonderful reasons why to put the data there and not have it go up to the cloud. But if the edge device is in you can plug it into the wall. If it's this camera over there in the corner of the building, I don't think this is a tinyML problem. This is an intelligent edge problem, which is very, very valuable. We can talk about IoT ecosystems, and we can talk about homomorphic encryption, and about training with differential privacy, and how to do personalization and warm start of these devices. And that's a whole other topic. I think that tinyML really happens when you need something that's small, it's battery powered. As I said before, maybe it fits in my body. Maybe this is in a drone, and therefore it has to be lightweight. So the drone has to fly itself, or detect something, find someone in the forest. So I think that so that we have this clarity, I think that these are two kind of related yet disjoint fields that we should talk about separately.
Agreed. I think we are talking about untethered devices basically, and likely battery operated devices. Still, you would be able to collect audio or potentially even images from that. And I think the issue of privacy still would come in, even in those cases. So how do you handle it for?
Just maybe to clarify, I was clearly speaking, when I talk about AR, VR, I'm clearly speaking about the glasses and the system with the glasses. And there, the glasses, tinyML is clearly giving some opportunities to improve the power, because you won't plug your glasses to the wall. You can't move the wall with you. So that is clearly something where tinyML could give a lot of benefit.
I'd like to pivot a little bit to a question about what the impact is on entrepreneurship and new businesses and new kinds of companies. Now, it's routine and traditional to talk about disruptive technology, the implication being that when the technology changes in a fundamental way, it creates a small amount of creative chaos in which presumably some new business models, some new enterprises, some startups can find niches and grow. Can you speculate a little bit about what about the tinyML technology or ecosystem or applications favor big companies who are applying it to do what they do versus new enterprises who can wedge their way in somehow into the ecosystem of players?
So one thing that comes to my mind is the generation of labeled data. So if I look at our use cases, we sometimes have a use case in mind that we think we can apply those techniques to it, but then we actually need data in order to make the solution really good. And the data needs to be labeled. And what we often do is we use engineers and interns to generate some data to get a first impression, but that's not the right approach. And I could see if a small company offers this as a service, that we could call in and they can take whatever use case a big one thinks of and tackle it in a professional way and creates trustworthy labeled data for every kind of new use case. I think that would be valuable for the big companies, and we would pay for that.
So I don't know if it's for small companies or not, but what I see is that everything that is closer to sensors, everything that could be sold more than just the sensor, but everything computing, maybe spiking neural networks, very low power neural networks, whatever close to imagers, audio sensors, whatever, I think this is extremely valuable. And I'm pretty sure that everything that could be related also to multimodal sensors is something really important that we'll need definitely.
Yeah, maybe related to that, this may not be directly associated with machine learning, but on all of these systems, basically the total power matters. So I think someone was presenting yesterday that the microphone, I think was actually Dennis presenting that the microphone that they got from InvenSense, if they use the front end of that, it burned a few milliamps of power and totally overwhelmed the total budget. So they had to take only the resonator and design a completely different circuit front end for that, so it would go down to microamp. So it is your sensor interfaces, is the rest of your IC, is your power management, is your communication, and your machine learning algorithm that eventually allows the system to be to the level that you can wear it and would run off of a, I don't know, 30 milliamp hour battery and would last for weeks or months. So I think the overall system solutions and startup companies that can come up with system solutions, I think would have a good position.
So I think that the big companies are really, really good at building the platforms, and I think that it's a really great change that companies are now in the business of making tools and democratizing these technologies. I think that the thing that we are in shortage of, like what's the rarest commodity, and I think this has been uttered many times in this meeting, is just the idea, just the brilliant, oh, what's the great thing that I could build? And you don't need to have a computer science degree or any kind of expertise to think about that. So this is really something that really just needs creativity, needs people who live in the real world and face real problems and say, oh, wouldn't it be great if I had a gadget that does this? That kind of long tail behavior, I think, is something that big corporations actually don't do so well. And it's exactly something that the startup kind of culture and economy could really do, I think, brilliantly. I think, Zach, you made the comment that there won't be one big killer app, was it you? But there'll be multiple. And again, this is the long tail of ideas. So I think this is exactly something that a small group of 5 to 10 really passionate people can take all those tools written by the big corporations, use all the open source that's out there, and package it into a really brilliant idea, perhaps better than the big companies could.
And one of the things I've seen there is that with ML application, it is very often all about the data. And sometimes some small group recognizes, oh, there's some latent information in some information stream that they can get a hold of that nobody else is trying to harvest. And they find a way both to harvest it and to build some really interesting insight, some interesting business from that unusual mining, remining of some information stream. I'm really interested in this question about multimodal sensors that you brought up, Edith, because in the talks, I think yesterday, there really were not much in the multimodal sensors. I think maybe the Byteflies was the best example of that. But where do we think the unexpected opportunities may come from when we start putting together these different sensors? I mean, we kind of have the classic hits. We've got motion sensors, and we've got microphones, and we've got these low-end cameras to play with, and some other body sensors. But where do you put it together? And what are the new, unusual insights you get from having more than one sensor stream?
So it's a difficult question. I think that everything that you would want to be more context aware. So for example, I'm here in the Bay Area, I read a sign indicating San Francisco, and I hear people speaking English at the radio. I know immediately where I am. And this is something that sensors could bring, giving an immediate context of where you are. And this could already pre-compute a lot of information. Then maybe you don't need to hear more on the radio. You need just to compute the way where you want to go. It would really bring a lot of new information immediately to the system, and you would not need to compute everything coming from every sensor. So really this context that you need to know, it's something really important, and we don't know how to get the context today. It's really difficult. Human beings, they know how to do it very well, but it's very difficult just by using sensors to get the real context. So I think that's something important. Which sensors, whatever, I don't really know how to answer yet, but.
Maybe a down-to-earth example from a sensor person.
Yes, please.
So if you look at inertial sensors, like gyroscopes, for example, that are used in goggles, for example, they still have an offset issue. Even though industry has been worked on that for like decades, they still have an offset issue. If you combine it with a different sensor, like a camera, for example, you can combine the two signals and then calibrate each other so that over like medium terms, the offset issue goes away. And to just miniaturize that and make it super low power, I could imagine that can be also used for different applications. Like you use it in cell phones and you have a perfect navigation device that doesn't drift away with offset.
Good example.
Yeah, so I think that definitely is in the place when people use accelerometers and gyroscopes to correct each other's errors. But those are all rule-based approaches. The question is, can machine learning allow you to do better than that? And how do you do this multi-input basically systems for machine learning? I don't know what the state of the art is really in that area, if people are able actively to bring multiple inputs, right, and just one mode for the machine learning area.
All right. To finish up, I'm going to ask for one question from the audience. Okay, I have to make the transition, but I want to at least nominally include the rest of you. Yeah. So we have a question. Okay, back here.
Yeah, so I'm from TD Conventions. We make sensors, Excel, gyro, mag, pressure, microphones. So you know that. So now, my question is: so we want to put some computing, like context-aware algorithms on it, but we are not sure what kind of these algorithms shape or size would look like. Because if you put a full microcontroller on it, it's not a good use case for a sensor because it becomes a high power computing. So, and that's what we are struggling at. Do you want maybe quantization at that level, or do you want even the neural networks working at that level, or do you want just FFTs to be done there, or do you want a fusion to be done there with a GPS? So what kind of like computations you're looking at a multimodal sensor?
Yeah. Kind of the question.
Adam's presentation, he has a nice poster there. He does it with one lips.
Yeah, it's an important question to sort of to interpret it as raw sensors versus smart sensors, and what's the responsibility for the sensor maker to add the intelligence versus somebody who's further downstream.
So I think there it comes back to what Boris presented this morning on the chicken and egg. So I've been for 20 years on the egg side. Now I moved to the chicken side. Not that Facebook is a chicken or whatever. But really it makes these things much more clear now that I have all these applications requirements. Clearly it helps a lot. So of course, what we are using internally is AR, VR applications, but there are also some open source applications that you can use. And clearly having the big picture, it's really important what you're saying. Clearly having the big picture of what you should do, what the power breakdown is, it comes back to everything that is wireless. Maybe I try to gain 50% power in the neural network, but in reality, I have 90% of the power burnt by the wireless communication. And clearly getting the application will help to optimize the multi-sensor platform. And yeah, so getting an application is clearly what is the best to do.
I think we'll take one more
So I
question
just wanted
back
to make a comment about the multimodal sensors. Again, my group is has been working on the multimodal time series signals for actually a couple of years. And we were trying to actually make ourselves separate from the computer vision folks. And two key things actually we noticed with this, when you want to apply, for example, this CNN type of application networks to that. So one is the artifacts. A lot of these sensors, like the brain signals, they have a lot of artifacts. The other key features is that they're coming from a variety of frequency, right? So basically, there are different sampling frequencies. So when you want to use a CNN, which actually that's what we're doing as the raw input, put it to the CNN. So you need to make sure that you align all these signals from different modalities and from different sampling frequencies in such a way that you can actually capture the properties in a nice way. So we develop a sensor network. So that's what we call the sensor network that is very nicely captured for about 5 different multimodal sensor with real application, real data, which worked well. So I would be happy to give more information about that.
All right, I think we need to wrap up and make our transition to part 2 of this, lightning round of panels. So let's thank the panelists very much. Christoph,